Hi everyone, and welcome back to EasyEDA TWF channel. Today's video started after a good friend of mine asked this question.
Hey there, Frank. Ever since I got my Commodore PET 2001, I've always wondered why when I turn it off, there's a white dot on the screen that slowly fades away. It's rather bright and it kind of bugs me. I was wondering if you could help me figure out what's wrong with this thing, if anything, and perhaps there's a way to fix it.
Thanks for your question, Adrian. It's a good excuse to fix both of my PET monitors too. Of course, they show a similar dot at power off. Let's see what we can do to them. Actually, on my PETs, the dot appears a little later and lasts longer, but it isn't so bright. That's probably because of the different CRT we have. Here is the schematic of the 9 inches CRT monitor of the 2001 PET, which has been left almost unchanged also on all the 2001N second revision PETs. The PET main logic board sent to the monitor a few TTL digital signals that are needed for making the raster scan and the electron beam intensity modulation. As in a normal TV, the horizontal scan circuit also generates a few voltage supply rails needed for CRT operation. The vertical drive signal has a period of 16.66 milliseconds that corresponds to a frame rate of 60 Hz. The horizontal drive has a period of 64 microseconds that corresponds to a horizontal scan frequency of about 15.6 kHz. It is important to notice that the monitor has neither a vertical nor horizontal oscillators, so the raster scan and the secondary flyback voltage rails stop as soon as the PET mainboard has been turned off, as it can be observed in the still frame of the turn-off video that shows the raster scan collapsing. The last signal needed for the monitor operation is the intensity modulation. Since, how we said, we have only digital levels, the beam can only be full on when the drive signal goes low or fully extinguished when the drive goes high. So let's understand now what conditions need to exist for a spot to appear on a CRT. First of all, we need a high voltage on the CRT anode. That's the 10 kV supply coming from the flyback transformer. As we said, there is no horizontal scan right after we turn off the PET, but some high voltage charge remains stored into the CRT anode internal capacitance. Second, we still have a hot cathode, as its filament is directly fed with the main 12 volts monitor supply and not by a secondary supply coming from the flyback. This 12 volt rail has the biggest smoothing capacitor of all the monitor PCB, and basically after the raster circuit has stopped working, this capacitor can discharge almost only through the filament, keeping the CRT cathode hot for quite a long time. All the other CRT voltages like the grid 1 brightness bias, grid 2 cutoff and cathode bias are decaying too, but they can't make much of any difference on the spot anyway, as the last condition that must exist is also the only one that we can hope to change to avoid the spot itself. This last condition is an open path from cathode to ground to allow electrons to be emitted towards the CRT screen. Of course, the spot must exist, so we just need to find it and see if we can somehow block it after we turn off the PET. The cathode current first flows through R7 and R6. Then we have Q3's emitter that's in the wrong direction and CR6 anode that's instead forward biased. Then all paths through R4 have no ending to ground. CR5 is reverse biased, so the only possible way remains through Q2 if it can turn on, of course. Q2 can turn on only when Q1 is off and a sufficient voltage still exists on the 12 volt rail too. Q1 can be turned off by the PET TTL intensity signal But in this case, the PET logic board is already dead and can't have any role in this. Q1 will turn itself off when the 12-volt rail falls off a certain voltage because of the base voltage divider formed by R1, CR2, CR3 and R3. With some simple calculations using Ohm's law, we find that Q1 starts turning off when the 12-volt rail drops below about 7.7 volts, since its base voltage is then going below 0.7 volts. At this point, Q1 can't sink enough current anymore to keep Q2's base grounded, so Q2 will start conducting and the undeflected spot appears on the CRT. Q2 will keep conducting until the 12-volt rail drops below about 1.4 volts, since there is no voltage divider on its base circuit. Now we could be tempted to just add a resistor from Q2's base to ground to avoid it turning on after Q1 starts turning off. So let's see what value this resistor should have with a similar calculation as before. Turns out that this resistor should be 220 ohms or less. This isn't a good idea in my opinion, because it would change Q2's operating point quite enough, and this may not be a problem, but the other issue with this fix is that it would probably never work, as it would depend too much on the actual gain of both Q1 and Q2. They would be racing one against the other, and probably there would be still a voltage window to have Q2 conduct enough current to make the spot appear. If someone wants to try this route, however, can let me know how it goes in the comment section below. If we could instead block the current through R2 as soon as the 12-volt rail reaches, let's say, 8 or 9 volts, we could avoid the Q2 to turn on entirely. Of course, a resistor alone can't behave like this. So what we can try is using a zener diode plus a new resistor in place of the old R2. The zener will block the current flow when the voltage drops enough, and the new resistor can be calculated by making the new circuit still pass the same current as before when we subtract the zener voltage from the 12-volt supply. I then would add a small ceramic capacitor in parallel to the zener diode to smooth its internal noise, even if this video driver only works as an on-off switch, so the small zener noise is probably not making any visible effect. Enough theory now, it's time to test this workaround on the real monitor. So I made the zener capacitor and resistor little circuit. I removed R2 and installed it in my PET 3032 monitor PCB. First, I've tried to print this graphic character to see if the circuit change will maybe slow down the cathode driver, but except from focus effects from my video camera, I couldn't observe any visible problem. So the PET is now running a simple basic program that I wrote to fill all video with cycling characters. And I'm ready to power off and see what happens. So fingers crossed. Well. Seems fine. I don't see any spot appearing now. Well, very good. So it's time to tell Adrian about this good news.
Now the same things does the 2001 monitor, which I still didn't assemble into the complete computer, and just because this is not a fault but a design, let's call it feature. So if we power off, it must be a small dot, this one too, and as you can see it does. So let's apply the same fix on this monitor and see if it fixes also this one. Now since I didn't assemble the monitor, I don't need in this case to remove the PCB from the monitor case, and the resistor to remove is between these two solder joints. This one is the +12 and this is the other side of the resistor I want to substitute with the diode, the resistor and capacitor combination to fix the monitor. So let's see what happens after the modification and if it fixed this one too. Let's power off. Looks like, oh no, look at that. Look at that, it didn't fix. Now we have to understand what's the problem here. We have to understand what's the problem here. Interesting. Really interesting. Now before changing the actual zener diode voltage, let's understand if maybe this zener diode has a little current leakage at, for example, 6.5 volts. So I'm using a variable voltage supply, which is hooked to the zener and resistor combination, just measuring the power supply voltage that I set at 6.5 volts. And so if I place now the red LED of the multimeter in the junction between the diode and the resistor, I will see if there is any current flowing in this series of the zener diode and the resistor. If I measure exactly 0 volts across the resistor, there will be no current flow. If I measure something more than 0 volts, there will be some current flowing. So let's see what happens. So at 6.5 volts there is no current flowing, and let's see at what voltage I get current start flowing in this zener diode then. So now I'm turning up the voltage of the supply slightly, and you can see it start drawing currents. So let me back down the voltage from the power supply to obtain, yes, just a little fraction of a millivolt. This is 600 or 500 microvolts. So let's see what it means. So let's use the Ohm's law. Voltage is equal to resistance times the current, and we know that our resistor is 560 ohms, as you can see here, and we are measuring half a millivolt on the 200 millivolt VDC. So half millivolt is 500 microvolts, and so our current is the voltage divided by the resistance, so 500 microvolts, which is 5 times 10 at minus 4 divided by 560, which is roughly equal to 1 times 10 at minus 6, which is roughly 1 microamp. 1 microampere, which is really fine to display a small dot on a CRT. Now, last step is measuring the voltage out from the power supply and see if this zener diode is supposed to be conducting based on its turn-on voltage or not. Well, it's 7.9 volts. Now measuring the output of the power supply. which is, well, I don't know. I think it's surely okay for an 8.2 volt zener.
In order to better compare the actual leakage on different zener diodes, I need a very small current sink, the smallest one that I can make at home without buying very expensive instruments. So I fired LTspice circuit simulator and draw the simple 2-transistor current sink where I've used the biggest resistor I found in my parts bin, a 10 megohms one. At these very low current levels, a current sink like this will deviate quite a bit from the ideal behavior, because the base currents of the 2-transistor will be very similar to the collector current of Q2. So in theory this circuit should sink 60 nanoamperes, but the simulated circuit showed a 95 nanoampere value. This circuit will try to always sink the same current value regardless of the actual component we place as Q2 collector load. So if we put different zener diodes on Q2 collector, we can measure what voltage is needed on any particular zener to make it pass the same 95 nanoamperes current this circuit is made to sink. Of course, the higher the voltage we'll measure, the lower will be the leakage of that zener diode. So I quickly put together this simple circuit on a breadboard. First, to check that the circuit works as intended, I put a 1 megohms resistor as the collector load and measured the voltage drop across it, and that's approximately 110 millivolts. And applying the Ohm's law, if we divide 110 millivolts by 1 megohm, we find that the circuit is sinking 110 nanoamperes, which is enough close to the value predicted by LTspice. And anyway, the actual value is not very important. What matters is this is the same for all the devices we want to test. However, I forgot that I cannot use a cheap multimeter when I put a zener diode as the collector load. And the reason is that any low-cost multimeter has an input resistance of approximately 10 megohms. Like you can see in this image where I'm measuring one resistance multimeter with another one. The multimeter resistance goes in parallel with the zener diode and the test current ends flowing all into the multimeter resistance, giving a voltage drop of about 1.1 volts, preventing the high voltage zener diode to go into conduction. So, to measure the zener voltage drop at this low current, I do indeed need some more expensive test equipment, like for example a benchtop multimeter like the HP3456A. This multimeter has an input resistance of more than 10 at the power of 10 ohms. That's more than 10 gigohms resistance, which is more than enough for this job. Let's test now the zener diode that didn't cure the spot. It takes only a bit less than 7 volts to leak the 100 nanoampere current. So I found another 8.2 volt zener, this is an old Philips one, and soldered the resistor needed for the mod to it. This one needs almost 7.5 volts to leak the test current, which is half a volt more than the other one. And last test is a 9.1 volt random brand zener. This one needs almost 7.9 volts to pass the test current, but that's only half a volt more than the good 8.2 volt Philips zener.
So after all, I decided to try the 8.2 volts zener diode, which is different from the previous one, because the difference between the 100 nanoamp voltage and the nominal voltage was smaller than the 9.1 zener, and so I think what matters is not the actual nominal voltage, but how sharp it is, the transition. So let's see if I'm right and try to power off and see what happens. Well, it seems good. Don't want to speak too early, but yeah, it seems good. Fine. Now, yeah, pretty sure it solved the problem. Yeah, that was the marginal zener, so zener delta were not made equal.
Now I told Adrian about my fix, and he tried to install a similar fix on his monitor. This is the unmodified Adrian's monitor spot. As you are going to see, it appears earlier than on my own, and it's brighter too. On Adrian's monitor, however, the zener mode didn't seem to have any effect, even after he bought new zeners from DigiKey, since I warned him that some low-quality ones are unsuitable for this modification. So we started chasing ghosts for too much time. Out of desperation, I also suggested him to try to replace a lot of unneeded parts, as you can see on his video about the spot. However, finally I recollected that he tried to install a potentiometer on the focus grid, as I sketched here in this image. But this is a very easy path for the cathode current because the potentiometer just connects the 85 volts rail at ground. So finally Adrian removed that potentiometer, but that didn't completely fix the spot, although now is much different than before. The spot is now much dimmer and delayed, and Adrian also found that the more the PET was left powered on, the brighter the spot was. Also this time we spent a lot of time trying to figure out this issue. We had a big progress when another PET owner gave this PET to Adrian to be fixed. As you can see, it has a green phosphor CRT, like both of my PETs do. In this video, Adrian shows the still unmodified green CRT PET besides his modified white CRT1. What we discovered this time is that despite having the same analog board inside, these two modules have some parts value changed. In particular, C22 was the first one we noticed. Commodore engineers kept on increasing this capacitive value on 3 different revisions of the PET's monitor. On both my PETs I've got the 47 microfarad one. On Adrian's PET he found the 3.3 microfarad capacitor instead. Adrian also found that the green CRT PET had its spot completely fixed with the zener mode, and that swapping the green CRT analog board on his monitor makes the spot completely disappear too. So this clearly points to some differences in the boards. However, even after he substituted a 47 microfarad capacitor for C22, Adrian's monitor still had a faint and delayed spot that would get worse the more the PET was left powered on. Since connecting the green CRT analog board to the white CRT makes the spot disappear completely, there must be still some difference left. This time I had a good look at the different revision schematics for a possible hint. This is the difference I focused on. R5 was changed from 1.5 kΩ to 2.2 kΩ. R5 sets the current value through CR7, but this should not make any difference on the monitor at turn off. In fact, substituting a 2.2 kΩ resistors on Adrian's monitor didn't make any change on the faint spot. But then, why Commodore made this resistor change? Let's do some calculations on the current through the 33 volts zener. First, let's calculate the current that flows when Q2 is in the off state. This happens whenever the beam current is cut off and the black dot is scanned, or also when the beam is in the horizontal retrace periods or in the vertical retrace periods. Using Ohm's law, we find a current of 35 mA through CR7 in the best case, which is when the 85 volt rails is right at 85 volts, and 41 mA when this supply is actually 95 volts, as it's indicated on some schematics. These currents correspond to 1.1 watts power on the zener on the best case, up to 1.35 watts on the worst case. Let's observe that the zener diode is rated at 1 watt only. Now, doing the same calculations with a 2.2 kΩ resistor give 28 mA in the worst case, which is less than the previous best case. The power dissipated in the zener in this case is about 0.93 watts, or even less if the 85 volt rail is less than the maximum value. What happens when Q2 is turned on, which is when a bright portion of the screen is scanned, is that current flows through R4. This current is approximately 22 milliamps and it gets subtracted from the total current that flows on the 33 volt zener that we have just calculated. When the beam is on, the zener is dissipating about 0.4 to 0.6 watts with the 1.5 kilo ohm resistor, depending on the actual value of the 85 volt rail, or only 0.05 to 0.2 watts when R5 is 2.2 kilo ohms. The actual mean power dissipated on the zener depends on the actual ratio between dark and bright screen content. But we can easily understand that it's easy for the zener diode to run beyond its rated power levels for extended periods of time, when R5 is 1.5 kilo ohms resistor. In this case, CR7 gets too hot and it can degrade or even fail completely over time. That's why that resistor value was changed in later model revisions. So my hypothesis is that CR7 is often overheating during operations with the 1.5 kilo ohms resistor, and its junction degrades just enough to develop high leakage current, and that makes another path through CR6 and R4 for the cathode current after power has been turned off. This also would explain why the spot gets brighter the more the PET has been left on, since usually diode junctions leakage currents increase with temperature. So to eliminate this path, CR7 must be replaced with a new 33 volts 1 watt zener, and at the same time R5 changed to 2.2 kilo ohms 2 watt resistor. It took quite some time for Adrian to decide to test this last fix, but finally here is a clip of his own video that he sent me to be included here.
I've locked the focus, I've locked the exposure, and I turned off the studio light for maximum visibility of any potential spot. Here we go. Is it gonna work, or are we gonna have a spot? Would you look at that? No flippin' spot.
So this finally come to an end. Adrian first talked about this issue to me in the early 2020. So it's been a long project, but we both had other things going on anyway. This was an interesting journey and an opportunity to learn new things, at least to me. I want to thank Adrian again for spending a lot of time while we were trying to understand what was going on his monitor, and he never lost the faith we could find a good solution anyway. So I recommend watching Adrian's videos on this matter if you already haven't done so. You will find his side of the story and a lot of interesting details. And look on the video description to have links on the schematics, various other resources. I would recommend anyone who attempt this modification to leave comments on my video or Adrian's ones, so we are very curious to understand if it fixes other monitors as we did with ours. And until next time, thank you for watching.